Let's consider now another type of function. For every exponent p, we have a family of what are called power functions. So a power function is one where we have, linear stuff outside, and we have linear stuff inside, and then we have a single constant exponent. So a, b, h, and k can be any real numbers. P is the exponent. And so this is a family of functions with base function x to the p. Right? This is just a monomial. Only a single power of x is present. Every possible exponent gives us a different family of functions. So that means every possible exponent gives us a different shape of graph, slightly different domain and range. It turns out that we can consider power functions more or less together for this purpose. But exactly which exponent we have will affect exactly which family of functions we're talking about. And now in practice, when we're talking about power functions, we'll usually exclude the exponents 0 and 1. Why? Well, when the exponent is 0, our function is just x to the 0 power, which equals 1 everywhere except for x equals 0 itself. And so this is a constant function. So we don't need any of the complicated power function stuff for that. So we'll just not consider that one of the category of power functions. And when the exponent is 1, the base function is just x to the 1, which is just x, and that's linear. So again, we don't need any of our complicated power function materials for that. We'll just think of that as a linear function. Now, I was kind of vague before when I said every possible exponent. For now, we're going to limit our discussion to positive integer exponents. But eventually, we'll consider all rational numbers as possible exponents, and remark really briefly on what it might mean to put an irrational number in the exponent as well.